Hi there. In this video, we'll be talking about the concept of specific heat, both kind of what it means and then how we can use the equation associated with specific heat to help us answer some chemistry-related problems, right? So first, what is specific heat? Well, before we answer that, let's go back even a little bit further and think about what heat is, right? So heat is a kind of energy that can flow in and out of matter. And when that transfer of energy in or out, that heat energy in or out of matter occurs, we experience, if we interact with that matter, we experience the change in temperature. So if heat flows into an object and then we touch that object will feel hotter to us. Its temperature has increased, right? If heat flows out of an object that we then grab a hold of, that object will feel colder to us, right? So heat is flowing into or out of matter, right? And that causes a temperature change. Well, what if we had a small bit of matter and then a really big bit of matter, right? And so if we take the same amount of heat and put it into a really tiny piece of matter, okay, we'll probably see, a kind of a big temperature change or a larger temperature change than if we took that same amount of heat and put it into a really big piece of matter, right? So that heat is going to spread itself out through that really big piece of matter, and then that temperature change that we experience will be a little bit smaller. So there's a relationship there between the heat that's added or removed, say for now, let's say added, the heat that's added, and the amount of matter that we have. So how do we define the amount of matter? Well, we'll define it by mass, okay? So there's a relationship between heat, mass, okay, the mass of that matter, and the temperature at which that matter exists, okay? So as heat flows into an object, its temperature will change, right? Okay, so there's this relationship here between heat, mass, and temperature. And that relationship forms what's called specific heat, okay? Which for the purpose of this video, I'm going to abbreviate as S sub P, okay? Different chemistry textbooks, different chemistry teachers may have their own abbreviation. For me, what typically works is S sub P, all right? And so what this idea of specific heat says, it says, okay, if I want to cause the temperature of a certain amount of matter to increase, I'm going to need to add a certain amount of heat, okay? And in fact, one of the units of heat energy is actually defined by thinking about this idea of specific heat. That unit is called the calorie, okay? So calorie with a lowercase c, abbreviated CAL, one calorie is defined as the amount of heat that's required to make 1 gram of water, okay, increase its temperature by 1 degree Celsius, okay? So 1 calorie is the amount of heat that's required to raise 1 gram of water 1 degree Celsius. Okay? And so we see this relationship here between heat, mass, and temperature. Let's think this through a little bit. Let's say we wanted to raise 2 grams of water by 1 degree Celsius. Well, it takes 1 calorie to raise 1 gram by 1 degree Celsius. So how many calories would we think that it would take to raise 2 grams by 1 degree Celsius? Well, it would take twice as much heat, right? So 2 calories would raise 2 grams of water by 1 degree Celsius, right? What if we had 10 grams, okay? So if we had 10 grams of water, it would take 10 calories, right? 10 calories would raise 10 grams of water by 1 degree Celsius. So there's this kind of multiplicative relationship here between heat and mass, okay? What if we think about it the other way? What if we stick with 1 gram of water, but we want to take that 1 gram of water and instead of raising it by 1 degree Celsius, let's raise it by 2 degrees Celsius, okay? So how much heat would be required to raise 1 gram of water by 2 degrees Celsius? Well, again, it would be twice as much heat. So 2 calories would raise 1 gram of water by 2 degrees Celsius, okay? What if I wanted to take that 1 gram of water, okay, and raise it by 10 degrees Celsius? Well, it would take 10 calories. 10 calories would raise 1 gram of water by 10 degrees Celsius. So again, there's that kind of multiplicative relationship between heat and temperature. So there's a multiplicative relationship here, there's a multiplicative relationship here. And so thinking about these two ideas gets us to this specific heat equation, okay? And so what we can say is that heat, okay, heat is equal to the mass of an object, okay, times multiplied by its change in temperature, multiplied by its specific heat, right? Remember, for this triangle here, I used specific heat to define the vertices of this triangle, right? For water, 1 calorie will raise 1 gram, 1 degree Celsius. So if I want to think about how much heat is required to change the temperature of an object, okay, I need to know what's the specific heat of that object, okay, what's the relationship between heat, mass, and temperature, what's the mass of that object that I have, and what's the temperature change that I'm trying to affect, okay? So having these bits of information allow us to do some pretty cool calculations, okay? Little pun there. All right, so calorie is one of those units of heat. Another unit of heat that's used quite often in chemistry is the joule. Okay, and so what you see here, the relationship between calories and joules is that 1 calorie is equal to 4.184 joules, right? So this equality can be used as a conversion factor to convert from joules to calories or from calories to joules, right? And so if we think about that idea, this equality here, and we think about the specific heat of water, well, the specific heat of water is 1 calorie per gram per degree Celsius. Okay. It's also 4.184 joules per gram per degree Celsius, right? So the amount of heat that's required to raise 1 gram of water by 1 degree Celsius is 4.184 joules, okay? Now, just one little clarification here. If you think you've heard the unit calorie before, well, you probably have, right? So dietary calories are what's used to describe the energy that's in a particular food item that we might consume, right? And so I just want to make clear that that calorie that's listed on the box is a little different than what we're talking about. So calories on a container of something that's listed there, it says calories with a capital C. And that's dietary calories. And what we find is that 1 dietary calorie is equal to 1,000 of these calories that we're talking about, okay? So the amount of heat that's required to raise 1 gram, 1 degree Celsius is really tiny, okay? It's really tiny compared to a calorie that we might consume. All right, well, let's think about this. How might we use this equation here, okay? So, let me write a problem up here on the board, and then let's give it a shot. All right, so here's a problem here. How many joules are required to heat 500 grams of water from 24 degrees Celsius to 65 degrees Celsius? Okay, and so in order to solve this problem, I need to use this equation here. And so what I should do is figure out, well, which of these variables do I have, and which of these variables am I trying to solve for, right? So let's think about that. We're asked how many joules, okay? How much heat, right? How much heat? So heat is probably the thing that we're looking for, okay? Let's see if that makes sense. Are required to heat 500 grams of water, okay? So we're told 2 things right there. Heat 500 grams of water. We're told what the substance is and how much we have of it, okay? That tells us 2 things. It tells us the mass, okay? It tells us the mass of our substance, but it also tells us what it is, and that's important because every substance has its own specific heat. Okay, so it's 500 grams of water. That 500 grams of water okay, means that specific heat in this problem is going to be the specific heat of water, right? Which we're given here. The specific heat of water is 4.184 joules per gram per degree Celsius, okay? Why did I choose that one? Well, because we're asked how many joules, okay? So heat is going to be in joules. What we're going to solve for is going to be in joules, right? And so if we want to try to solve for joules, then we want to use the specific heat that's got joules in it, right? And so specific heat here is 4.184 joules per gram per degree Celsius, okay? All right, so I know the mass, I know the specific heat, I know that I'm trying to get to heat, so I need a change in temperature. Well, what's my change in temperature here? Well, I know that I want to heat the water from 24 degrees to 65 degrees, okay? So my initial temperature, T sub I, is 24 degrees Celsius. My final temperature after the water is heated is 65 degrees Celsius, okay? So what's my change in temperature? Change in temperature is going to equal TF minus TI, right? Where I'm going minus where I started, okay? So 65 minus 24, right, is going to be 41 degrees Celsius. So delta T is equal to 41 degrees Celsius. Okay, so now I know my mass, I know my change in temperature, and I know my specific heat. So by knowing those three things, I can calculate how many joules would be required, right? And so the math here that I would need to do, heat is going to be equal to 500 grams times 41 degrees Celsius times 4.184 joules per gram per degree Celsius, okay? So let's put all this together before we actually use our calculator here. And so what I can say is that heat is going to be equal to 500 grams times 41 degrees Celsius times 4.184 joules divided by the units of grams and degrees Celsius, right? Because specific heat is joules over grams and degrees Celsius because it's joules per gram and joules per degree Celsius, okay? So when I put all these numbers together, the joules will stay in the numerator here. The grams and degrees Celsius will go in the denominator. So when I have all this stuff together, look what is happening to my units here. I'm going to have grams from mass, okay, and grams from the mass of our water and grams from specific heat will cancel, okay? Degrees Celsius from our delta T and degrees Celsius from specific heat will cancel. And so the only unit that I'm left with here is the unit of joules. And remember, that's the unit that I'm looking for. It's how many joules, okay? So by using specific heat, right, we want to make sure that our mass is going to be in the same units that shows up in specific heat. We want to make sure that our temperature change shows up in the same units that we see in specific heat. And the reason for that is because those units will cancel out, leaving us only with the units for heat. All right? So let's do that math. So I can say 500 times 41 times 4.184 equals 85,772. Okay? So the heat that's required to raise 500 grams of water, 41 degrees Celsius, is 85,772 joules. Okay? All right, let me erase the board here and we'll try another problem. Okay, I've erased the board and put up a new problem here. So how many joules, how much heat? Okay, so again, we're going to be asking how much heat in joules are removed from 350 grams of gold. Okay, so again, we know our mass and our substance. Okay, So our mass here is going to be the 350 grams of gold. And so because we have gold, we need a specific heat of gold. Okay, well, luckily I wrote it on the board, right? So the specific heat of gold is 0.129 joules per gram per degree Celsius. One thing to note here, look how small this number is here compared to the number for the specific heat of water. It takes a lot more heat, okay, to raise a gram of water 1 degree Celsius than it does to raise a gram of gold 1 degree Celsius. Okay? So our specific heat here for gold is going to be 0.129 joules per gram degree Celsius. Okay? So again, I'm going to need our change in temperature. Well, the change in temperature says that the gold is cooling from 70 to 20 degrees. Okay? So Celsius. So what's my change in temperature? Well, I need my final temperature. My final temperature is 20 degrees Celsius. Right? My initial temperature, where it starts from, is 70 degrees Celsius. Okay? My metal is cooling from 70 to 20. Well, delta T is going to equal TF minus TI, right? Where it ends up minus where it started. So 20 minus 70, of course these are degrees Celsius, 20 minus 70, our change in temperature is going to be minus 50 degrees Celsius. Okay, minus 50 degrees Celsius, right? And so we have a minus sign now in our change in temperature. That's going to mean our answer is going to have a minus sign in it. We'll talk about that in a second. But for now, let's solve this. Let's go ahead and solve this problem. So we know that heat is what we're searching for. So our number of joules is going to be equal to 350 grams times minus 50 degrees Celsius times 0.129 joules per gram degree Celsius. Okay? And remember, we got grams in the numerator and the denominator, so those will cancel. We've got degrees Celsius in the numerator and the denominator, so those will cancel. Our only unit that's going to be left is joules, and that's what we're looking for, right? So let's do that math. So we can say 350 times negative 50 times 0.129. Okay, and our answer here is negative 2,257.5. Right? So 2,257.5 joules, and you notice that was negative. Okay, so negative 2,257.5 joules. Well, how can you have a negative heat? How can you have negative energy? Okay. The positive and the negative, it gets a little sloppy, but the idea is that the negative sign or the positive sign, what they're there to define is the direction of that heat flow. Okay? Remember from our last problem, heat was positive. Okay? But that, in our last problem, heat was entering the water. We were trying to heat it up. Here, we're trying to cool, or the gold is cooling down. Okay? And so in order for the gold to cool down, heat has to be removed. Okay? Heat is removed from our object. So minus heat in this context means heat that's removed from an object. Positive heat means heat that is put into an object. And like I said, it gets a little sloppy. That negative or positive sign usually means direction, but it changes based on the scenario. And so that's one that you'll just kind of have to get a little comfortable with, whether it's positive or negative, depending on the scenario. In fact, I'm going to erase the board. We'll do one more problem, a little more complex problem, and it's really going to kind of test our patience in terms of that positive versus negative. Okay? Okay, so I've put our last problem here on the board. We're told that we've got 26 grams of gold, and that gold has been heated to 300 degrees Celsius, right? And then we've also got this container of water, this insulated jar containing 100 grams of water, and that water is at 25 degrees Celsius, right? So we have this insulated container of water, 100 grams of water, and we're taking this hot chunk of gold and we're putting it into the water, right? And then we're going to allow this system to come to equilibrium, okay? Right, the hot metal is in cool water, so the metal's going to cool down. And as it cools down, it's going to warm up the water, right? Because heat flows from hot things into cool things. So heat is going to flow from the gold to the water until they're both at the same temperature. So the question is, what will be the final temperature of both the gold and the water once the gold has transferred its heat to the water, okay? So this is a really common problem that if you're taking a chemistry class, you might do this in lab. Maybe not with gold and maybe not with a metal that's been heated up to 300 degrees, but some experiment like this. And so you need to be able to figure out, well, if I know what the initial conditions of both the metal and the water are, can I figure out what the final conditions are? And the reason that this works is because of this idea that when we put the metal into the water, the heat that's leaving the metal or leaving the gold is going to be the heat that's entering the water, okay? Heat leaves the metal, it enters the water. So the heat, which I'm going to call Q, okay? Q gold, the heat that's leaving the gold, is going to equal Q, the heat that's entering the water. And remember before what we said is that negative signs mean heat leaving, positive signs mean heat coming in, right? And so if we calculated the heat of gold as it cooled down, that would be a negative number. If we calculate the heat of water as it warms up, that number would be positive, okay? We want to end up with this equation here that says Q gold, the heat leaving the gold equals the heat entering the water. And so I'm going to put a negative sign here. And I'm going to put a negative sign here so that negative times a negative is a positive. And so that positive will then equal the positive heat going into water, okay? So a little tricky thing that we need to do there just to account for the negative temperatures or the negative heat that's associated with heat leaving the metal, okay? So how are we going to answer this question, right? Well, the first thing I think we should do is let's try to get all of our facts that we have right now, right? And we're going to build all of that on this notion that the heat leaving the gold is equal to the heat entering the water, right? So let's think about our water, and let's think about the gold, okay? Well, what things do we know? Well, we know that we're going to use this equation. So ultimately, we need to have as many of these variables as we can. And so we know that we're going to have a mass, a delta T, and delta T we know is the initial temperature and the final temperature, okay? We can subtract those to get delta T. And we need to know the specific heat of each of these things. Well, what things can we go ahead and answer? Well, we know the mass of the water. We're told that it's 100 grams of water. And we're told the mass of the gold. We're told that we have 26 grams of gold, right? We know the initial temperature of the water is 25 degrees Celsius. We know the initial temperature of the gold is 300 degrees Celsius, right? Final temperature, we don't know. Okay. And specific heat, we do know. We know that water specific heat is 4.184 joules per gram degree Celsius. And we know that gold's is 0.129 joules per gram degree Celsius, right? And so can we use the information that we have, right? Well, we know this idea that heat, right? The heat of the gold is going to equal the heat of the water. That means I can set up an equation for both mass times delta T times specific heat. I can set up an equation for both the water and the gold and then set them equal to each other because the heat of each of them has to be the same number, right? The heat that leaves the gold has to be the heat that enters the water, right? So let's do our two independent equations first, okay? We can say that the Q of water is going to equal 100, okay, times delta T, right? And remember, delta T is always going to be our final temperature minus our initial temperature. Delta T equals T sub F minus T sub I, right? So we can say delta T is going to be T sub F minus 25. And then we can multiply that by 4.184 joules per gram degrees Celsius. And of course, these temperatures should be in degrees Celsius. Okay. I can also write the Q of gold, right? The heat that's coming out of the gold is going to be the mass of gold, which will be 26 grams, right? Times the change in temperature, T sub F, I still don't know, but that's going to be TF minus 300, okay? And then multiplied by the specific heat of gold, which is our 0.129, okay? And remember, so now what I want to do is set these two equations equal to each other because Q water equals the negative of Q gold, right? So let's do that. I'm going to say that 100 times TF minus 25 times 4.184. I'm just dropping all the units just to make things a little cleaner, but we need to obviously keep units in mind here, right? So our Q of water is going to be equal to the negative of the Q of gold. Okay, so I'm going to put a negative sign here, and then I'm going to say 26 times TF minus 300 times 0.129. Okay, so here's my equation that I've set up by taking these two equations and setting them equal to each other because of this idea. And so now I have this equation, and the only variable in this equation is T sub F, which is what I'm looking for. What's the final temp? Okay, so now I just need to solve this problem, right? And so how am I going to solve this problem? Well, I'm going to do some of this multiplication, and then I'm going to try to get all the TFs on one side of the equation, all the numbers that don't have TF on the other side of the equation, and then be able to solve for TF, right? Okay, so let's give that a try. So let me bring up my calculator. And so what I'm going to do here is take 100 times 4.184. Well, that's 418.4, right? And I'm going to take that 418.4 and multiply it by both things that are inside the parentheses. Okay, so this is going to become 418.4 times TF minus 418.4 times 25. Okay, remember that 418.4 was 100 times 4.184 times 25. Okay, so 10,460. Right? And that's going to equal the same thing here. So I'm going to take my negative 26 and multiply it by 0.129. So 26 negative times 0.129, that equals negative 3.354. So negative 3.354 TF, okay? And then I'm going to take this number and multiply it by this negative 300 here. So times 300, that equals negative 1,006.2, right? So it's minus a negative. So minus a negative, that's going to be plus. So I'm going to say plus 1,006.2, okay? So negative 26 times 0.129 times 300 was a negative number, minus a negative number is a positive number, right? And so now I've got TF on both sides of the equation. I've got numbers that don't have a TF on both sides of the equation. So now let's get that all on the same side, right? So what I'm going to do here is I'm going to add negative 3.354 to both sides of the equation, right? Or I'm going to subtract negative 3.354 to both sides of the equation, and then I'm going to subtract, or I'm going to add 10,460 to both sides of the equation. Okay, so let's add the 3.354 to both sides of the equation. So I will take 418.4 and add to it 3.354, right? Subtracting a negative, okay? So 421.754 TF is equal to 1,006.2 plus 10,460, okay? 1,006.2 plus 10,460. That gives me 11,466.2, right? And now to solve for TF, I'm going to divide both sides of the equation by this 421 number. So I can say that TF is equal to this number, 11,466.2, divided by 421.754, okay? And that gives me 27, yeah, let's just say 27. Let's say 27 degrees Celsius, okay? So see what happened here. I took a really hot piece of metal and put it into, you know, kind of lukewarm water, right? And so what happens? That gold cools off a whole bunch and the water goes up just a tiny bit, right? They both end up being 27 degrees Celsius, okay? So that happens because water has a very high, comparatively high specific heat, let's just say 4 joules per gram degree Celsius, okay? And gold has a pretty low specific heat, let's say just 0.1 joules per gram per degree Celsius, okay? So the amount of heat that it takes to make gold's temperature go up, or the amount of heat that is released when gold's temperature goes down, is much less than the amount of heat that's required to raise the temperature of water, or the amount of heat that'll be released when water is cooled down, okay? So, like I said, this is a really common problem that you might experience in lab. It's a little tricky to think about, especially because of the kind of the positive and negative signs, but the thing to keep in mind is that the heat that this gold loses will be absorbed by the water, and the heat will travel from gold to water until their temperatures are the same, okay? All right, well, I hope this video was helpful, and I'll see you next time.